Hi guys. So let's try this video again. We're going to go over Chapter 9, the first learning objective within Chapter 9. So we're going to be looking at VSEPR, VSEPR theory, looking at it to predict our 3D molecular shapes. So just as a reminder about things that we see within a Lewis structure, as our VSEPR structures are going to be based on that Lewis structure, we've got atoms within these Lewis structures. Anytime we see lines, those are bonds. And then anytime we see dots, those are lone pair electrons. So we would say that these are bonds, and then these are lone pair electrons. So each one of them contain electron density. So they're like an area of electron density, if you will. So each one of these are areas of electron density. And when we're talking about a bond, those are two electrons that are shared between two atoms. And then when we're talking about a lone pair, that's a pair of electrons that are just on one atom, so they're unshared electrons. Okay. So in today's video lecture, we're going to be talking about VSEPR, which is valence shell electron pair repulsion. I'll tell you what that is in just a minute. But what it basically tells us is our molecular shape. So when we're talking about our molecular shape, we're talking about our atoms in 3D space, or our molecules in a 3D space. So we're taking a Lewis structure, which is two-dimensional, and we're applying electron repulsion rules, or looking at how electrons repel, to give us our VSEPR, which gives us a three-dimensional view of our structure. Okay. So the very first thing we're going to look at with our VSEPR model, well, first let's look at what VSEPR is. VSEPR is valence shell electron pair repulsion theory. So this theory is going to predict the molecular shape based on how electrons repel other electrons. And we are focusing on valence electrons, which is the same thing that Lewis structures focus on. So we're only looking at valence electrons because core electrons are going to be really tightly held to the nucleus, so they're not going to repel nearly as much. So with valence shell electron pair repulsion theory, we're going to first look at what's called an electron domain. So an electron domain is an area of electron density. So that area can be a bond, any type. So it could be a single bond, a double bond, or a triple bond, or it can be a lone pair of electrons, or non-bonding electrons. Okay. So these are going to be things that are going to repel each other. So in our VSEPR model, we're looking at electron domains around a central atom. And those number of electron domains around the central atom are going to dictate this structure. Okay, so um, we can look at electron domains around a central atom. And the other thing we're going to want to look at is what's called a bond angle. So if we've got some central atoms surrounded by two peripheral atoms, this angle made between the three atoms is called the bond angle. So with VSEPR, we're looking at our electron domains and we're looking at our bond angles. So the electron domains will determine the shape, and then from that shape we can determine what our bond angles are. And that'll tell us how close atoms are to each other and how they interact. So the first type of geometry that we look at with VSEPR is called electron domain geometry. And this is based on the number of electron domains. Okay, so we are going to start with a AB2 geometry, where A is our central atom and B are our electron domains. Okay, so our electron domains can be atoms or electron pairs, but we have our central atom and our two electron domains are going to look like this, where the furthest we can get those two electron domains away from each other is 180 degrees. So that is the furthest you can get two electron domains in space. And these electron domains can be atoms, as I've shown here, or we could also write one of them as an electron pair. Okay. In either case, we have an electron domain geometry. And I'm going to start writing electron domain as just ED. So this electron domain geometry, in this case, is going to be linear. And then as long as both of our atoms are bonds, then our bond angles are 180 degrees. Okay. Next electron domain geometry we look at is going to have an AB3 structure. So it's going to have one central atom surrounded by three electron domains. Like so. Each of these electron domains are going to be 120 degrees away from each other. So that's the furthest we can get those 3 electron domains in a 3-dimensional space. So if we look at this structure, this I'm just gonna kind of there we go. Something like that. Hopefully you see that this looks like a triangle. And it's all in one plane. All the atoms are in one plane. So we call this electron domain geometry. Trigonal planar. Okay, and here our bond angles are 120 degrees. We can also have one of our electron domains being replaced by an electron pair, and it would look like this. Okay, here we still have approximately 120 degree bond angle. Next, we're looking at AB4. So we have an A atom surrounded by 4 things, which we think would look like this. And if we looked at this, these would be 90-degree angles. This is incorrect. Because what we have to remember is we have a 3-dimensional space, right? So now we can go into a 3rd dimension and get our atoms or electron domains as far away as possible. And we would write this on paper by putting what we call a wedge and a dash. So any single lines means we're in this plane of the paper. Any wedge that we see means it's coming towards us. Any dash is going away from us. So this would be a big B, little b. And what this gives us is bond angles of 109.5. Okay. Now, I'm going to attempt to draw what this looks like. So we have one face of this structure, and then a second face of this structure, a third face of this structure, and a fourth face of this structure. So this structure has 4 faces, which is why it's called a tetrahedron, a structure with 4 faces, or tetrahedral. And here our bond angles are 109.5 degrees. Okay, and we can draw this where the atoms are replaced by lone pairs. Like so. Okay, but we still maintain approximately 109.5 degree angles. Okay. next geometry we're going to look at, we have an AB5 structure. So central atom surrounded by 5 electron domains. Like so. And here I want to point out that we have this right here and this right here. So we have some interesting things going on in the structure. So between our atoms in pink or electron domains in pink and those in blue, we have 90-degree bond angles. Between blue atoms, we have 120-degree bond angles, and then between our two pink, it's 180 degrees. So we don't really think about it as a bond angle quite as much, but those are 180 degrees from each other. Okay, so the things in pink, the atoms in pink, it's really just atoms. These are going to be axial. These are axial positions, or atoms. And then our atoms, or domains, should this be an electron pair, are going to be, it's going to be called equatorial positions. So if we have an atom in a B site, in a pink site, that'll be an axial atom. If we have an atom or domain in one of the blue sites, those would be in equatorial positions, or those would be considered equatorial atoms. Now, hopefully we see that if we've got an atom in sorry, let's actually put it right here. If we have an atom in a axial position, it is going to be 90 degrees from 3 atoms. So atoms in axial positions are 90 degrees from 3 electron domains. Okay. Atoms in equatorial positions are 90 degrees from 2 electron domains. Because of this, we always put we always put electron pairs in equatorial positions. So our equatorial positions have less repulsion. So our equatorial positions, because they're only 90 degrees from 2 other electron domains, they're 120 degrees from other ones, they are considered to be the less repelled position. So electron pairs are going to be going there. So let's just, real quick, do a little side note about the effective nuclear charge that a electron pair feels, whether it is going to be one that is a lone pair or if it's going to be a bonding pair. So non-bonding electrons only belong to one atom. Okay, so that means that they only feel the nuclear charge from one atom. This is different from our bonding pairs. So our bonding electrons feel the nuclear charge of two electrons, or sorry, the nuclear charge of two atoms. So they feel the nuclear charge of two atoms. So our bonding electrons feel a greater effective nuclear charge than non-bonding electrons. Okay, so if we think about some atom, if it has a lone pair, that lone pair is going to feel less of an effective nuclear charge, so it's going to spread out more. Versus if we have a pair of electrons between two atoms. So this can be contained more. So we would say that our non-bonding electrons repel more than bonding electrons. Which is why we want to put them in a position where they're going to have less things or be further away from things that have electron pairs. So they are always going to go onto our equatorial positions. Okay, back to the structure we were looking at. Okay, so here we have a triangle right there, or a triangle-based pyramid right there, and a triangle-based pyramid right here. So we have two triangle-based pyramids. So this electron domain geometry is called trigonal bipyramidal. Okay, our bond angles are 90 degrees and 120 degrees. So the 90 degrees is from axial equatorial, and then our 120 is equatorial equatorial. And as I said, when we take this structure and we put electron domains around it, we're going to put them on, or if we put electron pairs, we're going to put them on our equatorial positions, so they'd look like this. Like that. And like this. And like this. Okay. Last electron domain geometry we want to look at is a AB6 structure, so 6 electron domains around a central atom. So when we've got this geometry, when we've got our 6 electron domains around our central atom, it's going to look like this. We have our central atom A and our electron domains like so. Each one of these are going to be equivalent sites, and they're all going to be 90-degree bond angles. Another way you could draw this to get the same kind of geometry is like this, and some people prefer drawing it in this way, but we still have those 90-degree bond angles all around. So this is what we call an octahedral geometry, and what we see with this is we've got this base right here, and then on top of it we have one side, two sides, three sides, four sides on the top, and then on the bottom, one, two, three, four sides on the bottom as well. So this is a 8-sided structure. Which is why we call it octahedral. So here, our electron domain geometry is called octahedral. And our bond angles are 90 degrees each. Okay. Now, just like we've seen with our other structures, we can take our electrons and replace our sites. So let's look at what we get when we replace sites. So all of our sites are equivalent here, at least initially. So it doesn't really matter where we add these. So we could do like, and actually, I say that, but I'm going to draw it in a slightly different way. Okay, so this is one option, and we can take and replace another one of our electron groups with, replace that atom with a lone pair. At this point, because our electrons repel more than our bonding or non-bonding electrons repel more than our bonding electrons, we want to put our second pair of electrons as far away from our first pair, so it will go 180 degrees right there. Then our next one, it doesn't matter. We can put it wherever. So I'll put it right here. And then our last option will have to be 180 degrees away from our third electron pair. Like so. With each of these structures, because of our electron pair pushing more, our non-bonding electron pair pushing more than our bonding pair, we will get some less than 90 degree angles. So this one would be less than 90 degrees up here. These will actually be, since we've got equal repulsion from both sides, these bond angles will be 90 degrees. And then we go over to this next one. Because of this extra pair of electrons, this is going to be less than 90 degrees. And then for this last one, we'll actually have a bond angle of 180 because we've only got the 3 atoms and they're in a perfect line. Okay, so we've looked at all of our molecular geometries, all of our electron pair geometries or electron domain geometries. But I've drawn a bunch of shapes where I've replaced one or more of the atoms with electron pairs. And what we get when we do that is we get a structure that has a geometry that we can kind of describe in a different way. So we have what's called a molecular geometry. So a molecular geometry just describes the shape of the atoms within the structure. It doesn't say anything about the electron pairs, the non-bonding electrons. So molecular geometry describes the shape the atoms of the molecule make. So in the case of our structures where we don't have any electron pairs, our molecular geometry will be the same as our electron domain geometry because they're equivalent, right? They're both showing the same geometry because our structure has no lone pair. So in structures, where there are no non-bonding electron pairs around the central atom, the molecular geometry will be equivalent to the electron domain geometry. So they will be the same. So let's go through each of these structures and see how adding those electron pairs are going to change our molecular geometry versus what we saw with our electron domain geometry. So we're going to start with our linear electron domain geometry. And there's nothing we can do with this. If we've got a central atom and 2 peripheral atoms, this will have 180 degree bond angles. So we can't remove an atom and still really describe it by VSEPR, right? Because VSEPR talks about the shape of the bond angles. We will have structures where we have electrons replacing those atoms, but this is still just a linear geometry. So linear electron domain geometry and molecular geometry. So no matter what we do to that, our linear structure is going to stay as a linear structure. So when we start looking at our other electron domain geometry, so we go into trigonal planar electron domain geometry. We know we have this structure right here, and we have 120-degree bond angles. If we remove, or let's actually go with replace, so we're going to replace B with electron pair, and we get this right here. Here, because our electron pair is going to be more repulsive than our bonding electrons, this is going to be less than 120-degree bond angle. And looking at just the atoms of this structure, we get a bent molecular geometry. Next is our tetrahedral. I'm just going to put it as tetrahedral electron domain geometry. So just as a reminder what's going on, this wedge means we're coming out of the plane of the board. This dash is going into the plane of the board because we have a three-dimensional shape. So here, our molecular geometry is equal to tetrahedral. Same up here. Our molecular geometry is equal to trigonal planar. In structures where we have no electron pairs, the molecular geometry and the electron domain geometry will be the same. Now let's go and replace B with a lone pair, and we get this structure right here. And again, if we're looking at our structure, we get this right here. And so just looking at the atoms, ignoring that lone pair, we are going to have a trigonal pyramidal molecular geometry. And what we find, because of those bond angles, or because of that non-bonding pair of electrons, we are going to have a bond angle of 107 here. And this is a bond angle you need to know. So in a tetrahedral electron domain geometry, looking at our trigonal pyramidal molecular geometry, where we have one lone pair around our central atom, we have a bond angle of 107. And then we're going to go and replace another B with a lone pair. I'm going to draw this a little bit differently. Draw it like this. And what we get here, now we have two electron or non-bonding electron pairs pushing down. So we get a bond angle of 104.5, even decreased from here. Okay. And here we get back to that bent looking shape. So this is a bent molecular geometry. This is another bond angle you must know. So if you have a bent molecular geometry for tetrahedral, you need to know that that bond angle is 104.5. With the bent up here, just know that it is less than 120 for your trigonal planar. Next, we have our trigonal bipyramidal, TBP, electron domain geometry. So we've got our two pyramids on top of each other with their triangle bases. And here our molecular geometry is also trigonal bipyramidal because we have no lone pairs. We're going to replace B with a lone pair, and we get this structure right here. Here, this lone pair is going to be pushing, so this is going to be less than 90 degrees, and then this is going to be less than 120 degrees. You don't need to know exactly, just less than. Here, looking at this structure, it's called seesaw or sawhorse. And that's just the shape it kind of looks like if you're looking at it. If you flip it on its side, kind of looks like this, which kind of looks like a sawhorse. Or if you flip it the other way, kind of looks like what a seesaw would look like. So that's why they call it a seesaw or sawhorse. And then we're going to do that again. Remember, with our trigonal bipyramidal, we replace our equatorial positions, not our axial positions. So our next one is going to have another one of these equatorial positions replaced with an electron pair. I'm going to again draw this a little different. So I'm going to actually put my two lone pairs on these two equatorial sites, and I'm going to leave this one as my site where I put my B atom. And the reason that I did this is so you could see this shape that this makes. Here we have a T-shaped molecular geometry. And again, our electron pair is pushing, so this bond angle is going to be less than 90 degrees. Okay. Next one is our octahedral electron domain geometry. So we've got a regular one, and this one with our 90-degree bond angles, and our molecular geometry that is also octahedral. And then we start replacing. And because of that lone pair pushage, we get a bond angle that is less than 90 degrees. And this structure, we have a square base coming up to a pyramid type shape. So this is square pyramidal molecular geometry. Okay, and then replace again. Whenever we're replacing our second pair of electrons, or replacing our second atom with a pair of electrons, we want to minimize repulsion, so it'll go 180 degrees away from the first one. And looking at our structure, we have a square in one plane, so this is called square planar. Now, because we have our lone pairs 180 degrees away from each other, they're going to repel with the same amount of magnitude. So this bond angle will equal 90 degrees. So we're back to having a 90-degree bond angle. Okay, our next replacement of our B with a lone pair. Next one doesn't matter. I'm going to write this a little bit differently than I have been. So I'm going to go back to, I'm going to show you this one right here. So I'm going to use this one instead, just to let you guys see what the shape looks like. So here's those other lone pairs, and then doesn't really matter where the last one goes. So I'll just put it right there. And here we are going to have less than 90 degrees. And what we get is a T-shaped geometry. So our molecular geometry in this case is T-shaped. And then last one. Remember that you want to put your last pair of electrons 180 degrees away from the other one. We're back to an even, so we want everything to be 180 degrees from each other. So our bond angle here is 180 degrees, and all of our atoms are in one line, so this is a molecular geometry of linear. In the PowerPoint and on the worksheet, you can see a summary of all of the molecular geometries and electron domain geometries. So make sure to check those out so that you can kind of follow through and have a full summary of all the electron domain geometries and molecular geometries. Okay, so just a couple more things I want to talk about. One is degree of repulsion. So I talked about how our non-bonding electrons are going to repel more than others. So non-bonding electrons experience a lower effective nuclear charge. So because of that, they're going to spread out more and repel more. And then, of course, more electrons are going to repel more. So our non-bonding electrons are going to repel the most. But a triple bond is going to repel more than a double bond, which is going to repel more than a single bond. So when we look at For instance, CH4 we have bond angles of 109.5. When we look at NH3, we have bond angles of 107. And then if we look at water, we have bond angles of 104.5. So more electrons, more repulsion. And then when we look at something like this structure, this double bond, because there are 4 electrons instead of just 2, they're going to repel more than the others. So this bond angle right here and here is going to be greater than 120 degrees. And this one is going to be less than 120 degrees. Specifically, these two are 124.3 degree bond angles, and then this one is 111.4 degrees. You don't need to memorize those. You just need to memorize these. And know that if you have different types of bonds, they're going to repel differently. So you should understand the ordering and understand and know what your bond angles for your tetrahedral ones are. Last thing I want to talk about is the idea of a multiple central atoms, or the idea of multiple central atoms. So a central atom is one that has 2 or more atoms bonded to it. So anything that has 2 or more atoms is considered a central atom. And we're going to look at things with multiple central atoms. The big things we're going to look at with multiple central atoms are organic compounds. So the nice thing about organic compounds is they kind of top out at tetrahedral shapes because we're talking about carbon. Carbon is in group, it's in period 2. So it doesn't have those available d orbitals, so it can't expand its octet. You have to be in period 3 or below to expand its octet, and organic compounds are a bunch of carbons which cannot. So we're looking at 4 bonds or less. So when we're looking at our multiple central atoms, generally what I'm going to give you is a condensed structural formula. Which is a formula that shows what the order of atom attachment is. Okay, so I'm going to do a couple of examples real quick. So CH3, CH2OH, CH3, 4C, HOCH2, CH2OH, and then CH3, CO, in parentheses, CH3. So let me show you how each of these work. So the hydrogens are always going to be peripheral atoms. So you're looking at the atoms that are actually here. So this carbon, and this oxygen are going to be considered central atoms, and then the hydrogens are going to be kind of hanging around them. So the first carbon is attached to the second carbon is attached to the oxygen. So we would write it as carbon, carbon, oxygen. Then we'll put in our hydrogens. So we have 3 hydrogens on the first one, 1, 2, 3. 2 hydrogens on the second one, 1, 2. And then 1 hydrogen on the oxygen, like so. After that, you're just going to fill in electrons on your oxygen to reach an octet. Okay? And if you were to count all the electrons, you'd find that this is correct. Okay, so here we have 3 central atoms. Each one has 4 electron groups. Or electron domains. So they're all tetrahedral electron domain geometries. The 2 carbons, all the electron domains are bonds, so they have a molecular geometry that is also tetrahedral. And then this oxygen has 2 lone pairs, so it has a molecular geometry that is bent. From this information, we know that our 2 carbons have bond angles of 109.5, and our oxygen has a bond angle of 104.5. Next one, we've got this carbon, and it's going to be attached to this carbon. But make note that there is this 4 right here. That means that there are 4 of these CH3 groups that are surrounding this central carbon right here. So 1 carbon with 4 CH3 groups around it, like so, and then add in those hydrogens. There we go. And every single one of these carbons is a central atom. They all have 4 electron domains, and they have no lone pairs. So our electron domain geometries are all tetrahedral. Our molecular geometries are all tetrahedral. And all the bond angles are 109.5. Next one. This oxygen connected this carbon, connected this carbon, connected this oxygen. And then we put in our hydrogens. The first oxygen has 1 hydrogen. The carbon has 2 hydrogens. The next carbon has 2 hydrogens. And then the last oxygen has 1 hydrogen. Add those electron pairs in. And voila. Here, our carbons again are going to have a molecular domain geometry, or electron domain geometry, and a molecular geometry of tetrahedral, so they'll have 109.5 bond angles. And then our oxygens are both going to be bent molecular geometries, so they're going to have 104.5 degree bond angles. Okay, next one. We've got this carbon attached to this carbon, attached to this carbon. This one, oxygen right here, is in parentheses. So that means it only belongs to that carbon right there, and it's going to be bonded as a double bond. So we have our carbon, 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 double bonded oxygen, and then put in our hydrogens. And then electron pairs. So this oxygen in this particular case is not a central atom because it only has 1 bond. This carbon, however, only has 3 electron domains. So this carbon has a trigonal planar electron domain geometry and molecular geometry. So this bond angle right here is less than 120 degrees. It's less than 120 degrees because of this double bond right here. So this Angle right here is going to be greater than 120 degrees. And then the rest of them will be 109.5. Okay, that is everything. Thank you guys for making it through this incredibly long video. Sorry that there's so much in this particular um, learning objective, and I will see you guys later.